So, welcome students to our series of lectures that we are doing for IOKM Olympiad Geometry. So, in we have already covered things related to triangles, and in this lecture we will be primarily covering topics of quadrilateral, the topic of quadrilateral. So, we have gone through similar triangles, we have gone through congruent triangles, we have gone through triangle inequalities, we have gone through Thales theorem, midpoint theorem, and things like that. Okay. Now, moving ahead, today's topic is quadrilaterals. Once we are through with quadrilateral followed by circles, then we would be covering up the variety of problems that is actually appearing in the that will actually be appearing in the examination. Okay. Now, quadrilateral is a polygon of four sides. A quadrilateral can be of this shape or this shape. Okay, this is a convex quadrilateral. And this is a concave quadrilateral. Now, in convex quadrilateral, all the angles are less than 180 degree, and in a concave quadrilateral, see, this angle is greater than 180 degree. Some very elementary facts that you must understand is that the sum of angles of a quadrilateral is 180 degree. You can see you are getting this triangle and this triangle. So, first and foremost is sum of angles of a quadrilateral is 360 degrees. Even in the case of a concave quadrilateral, that will be the case. Fine. Now, we generally discuss convex quadrilaterals only. Most of the properties, most of the things that we come across, that we know, are things related to convex quadrilateral. Unless specified, we treat quadrilaterals as convex quadrilaterals. Even though it is expected that it is always explicitly told which is the quadrilateral that we are dealing with, but invariably a conventional way is to deal a quadrilateral as a convex quadrilateral. Okay. Now, what are some of the quadrilaterals that you go through? So, a very important quadrilateral is trapezium. Okay. So, what you say in a trapezium, one pair of opposite sides. Okay, one pair of opposite sides are parallel. Okay, one pair of opposite sides are parallel. Now, what you can possibly say is that in a trapezium, see, as a consequence of it, what do you get? See, these two angles are equal. This angle is equal to this angle, and therefore this angle has to be equal. So, if this is P, intersection point of what we say, the line joining the alternate vertices, we call them diagonals. These two triangles are similar. So, one of the things is that divide each other in same ratio. Okay, in a trapezium. And it is also the other way around. If diagonals divide each other in the same ratio, then the trapezium is a, then the quadrilateral is a trapezium. Further, we say that area, if this triangle has area delta 1 and this is delta 2, then delta 1 is equal to delta 2. And we did it last time, if you remember, this is root of delta 3 delta 4. So please have this in mind. In last class, if you remember, if you see the video of last class, we explicitly used it. Further, moving ahead, in a trapezium, if we have the line joining the midpoints of non-parallel sides, EF. Okay, so EF is called median of this trapezium. EF is midpoint of this trapezium. Further, EF is parallel to parallel sides and EF is half their sum. It is parallel to the parallel sides and equals half their sum. These three are these are parallel sides of a trapezium and this would be parallel to it. Okay. Now further you can also add here if suppose this is G and this is H. Okay. So GH is AB this will also be the midpoint. Okay, once we come to parallelogram, we will be proving. This is basically the converse of Thales theorem, midpoint theorem. The converse of midpoint theorem is giving this. You can see from this point you are drawing a line parallel to this, so it will be bisecting AC also, it will bisecting AB also. Okay. And insofar as length is concerned, you can say this is half and this is also half of AB. This is half of AB, this is half of AC. So what is this? Half of this minus this, from converse of midpoint theorem or basic proportionality theorem or Thales theorem. Okay. So these are the facts that we need to know about trapezium. Okay. We have gone through areas too. So moving ahead now, say somebody says, suppose I give you something related to trapezium, a question, let us solve a question regarding trapezium. Okay. Suppose this length is L, this length is M. Suppose we extend it and They meet at some point. Now from here we draw a line parallel to the parallel sides. So let us name it A, B, C, D, E, F. So if L is 10, let me give you, or let us be in terms of expression only. Find EF in terms of L and M. So I have deliberately omitted the language part. The language would have been ABCD is a trapezium. The non-parallel sides are further extended to meet at a point P. From P, a line is drawn parallel to the parallel sides. The diagonals are extended to meet this line drawn, this parallel line drawn at E and F. Find the length EF. So that language part I have drawn the diagram right in front of you so as to save some time. Now, so much parallelism is involved, you can possibly think of it as question where a lot of angles are going to be equal since we are dealing with parallel lines. So, a similar triangle notion can be used. This is a triangle, these two triangles are similar, you can see. And of course, if this L and M are known, okay, we can find the proportionality part here also, isn't it? So, what should we do? Suppose this length is x. So, what can we say? PC, this is PC, this is opposite to this angle, upon BC. Okay, is equal to PC. Opposite to this angle is x upon L. PC upon BC. Now, can we find the ratio PC upon BC? Because these two triangles are similar. So, what will PC by BC be? You can say PC by PB is M upon L. Now, PB is PC plus BC. Is M upon L. Fine. So, you can say BC upon PC plus 1 to BC upon PC. PC upon BC is so you can write X as LM upon L minus M. And very simply you can say this is going to be the same here also. So this is also going to be Lm upon L minus M. I hope you are able to fathom this. These two triangles are going to be similar and the same ratios are going to come. So EF is nothing but, what is EF? Two Lm upon L minus M. This is the length EF. So we could have done it earlier also using similar triangles only, but to use the terminology of trapezium, we deliberately are doing it here only. Okay. Now, suppose somebody says in a trapezium, in a trapezium, this ratio is 2:3. Diagonals are dividing in the ratio 2:3, and this has area 16. Find area of trapezium this triangle has area 16. So this is again 2:3. Diagonals are dividing each other in the same ratio. This is a trapezium. So we can very easily understand how these ratios are going to be. This area is going to be in the squares of ratios of sides because the triangles are similar. So if this is delta, delta upon 16 is, so delta is 36. This is 36. And what is this area we have read? Root of delta 1, delta 2. 4 into 6, 24. What is this area? 24. So the total area of this trapezium is 52 and 48, that is 100 square units. Okay. Moving ahead, we have a parallelogram. What do you have in a parallelogram? Both pair of sides are parallel. Special case of trapezium. Both pair of sides are parallel. Okay. Further, the opposite sides are equal in length. AB is parallel to CD. BC is parallel to AD. Further, AB is equal to CD and BC is equal to AD. Very, very, very important property is diagonals bisect each other. Diagonals bisect each other. This, please remember, is necessary and sufficient for a parallelogram. Please remember it. It is a very, 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 very important property. In a parallelogram, diagonals necessarily bisect each other. In a parallelogram, diagonals necessarily bisect each other. And if diagonals bisect each other, it is a parallelogram. So for sufficiency, insofar as necessity is concerned, it is very trivial. Since these two are similar, these two sides are equal, so this will be equal to this to this. Okay, and by diagonals bisect each other, we can say that if diagonals bisect each other, these two triangles are going to be congruent triangles. You can very easily see this is equal to this is equal to this, these two angles are definitely equal. So, this angle will be equal to this angle will be equal to this angle, hence the opposite sides are parallel. Okay. So, will be the case here. So, one pair of sides being equal and parallel, but what is mostly used, you will be very often using it is this. So, you can see that just there is a step more. In trapezium, what we have said, diagonals bisect each other in the same ratio. If that same ratio is 1:1, it becomes a, what does it become? It becomes a parallelogram. In a trapezium, what we are saying, diagonals divide each other in the same ratio. If that ratio becomes 1:1, you get a parallelogram. One pair of sides being equal and parallel is sufficient for parallelogram. Okay. Sides, one pair of sides being parallel and equal is sufficient for a parallelogram. Sufficiency part, please keep in mind. Sometimes if we have to justify that a quadrilateral is a parallelogram, we just say that since diagonals bisect each other, it is therefore a parallelogram. Diagonals are not equal in length, as you can see in a parallelogram. Now, if you are able to see that all the four triangles are of equal area in a parallelogram, or these two, okay. A diagonal divides a parallelogram into two triangles of equal areas. You can see this and this. These two triangles are going to be congruent. So, a lot of times bisection plays a very important role in proving this. Converse, for example, converse of basic proportionality theorem is generally done through converse of basic proportionality theorem is generally done through the Thales theorem that you go through is generally done through this only. Okay. Now, we must be well versed in utilizing them. Suppose somebody is asking us regarding, say, show that centroid divides medians of a triangle in the ratio we had just used it as a fact earlier. There are various proofs available. I am using the proof which utilizes the diagonals of a parallelogram bisect each other. D, E, F. Okay. We have to show AG is to GD is is to 1. Fine. So how would we go about it? We extend GD to EFG to say some point K. Extend GD to K such that GD is equal to KD. Now look at it very carefully. What are we going to do? See, these two are definitely equal. We have extended it like this, so we can safely say therefore BKCG. In quadrilateral BKCG, diagonals bisect each other. Okay, in quadrilateral BKCG, diagonals bisect each other. Hence, it is a parallelogram. Hence, it is a parallelogram. Now, if you look at it now properly, see triangles. Now, triangles AFG and ABK. See again, this we have shown that they are parallel, are similar. Therefore, by midpoint theorem, okay. See AF by AB, or let us now write only by corollary, we can say by corollary of Thales theorem or basic proportionality theorem. Let me write by corollary of basic proportionality theorem, AF upon BF is AG upon GK, which is 1, since this is the midpoint. So AG is equal to GK. GK is 2 times GD. So AG is to GD is 2 is to 1. This is one proof where we are using parallelograms. So medians are divided in the ratio 2 is to 1. Okay. Further, we should also keep in mind that in a triangle, this triangle, and this triangle, medians divide the triangle like this. These 3 triangles are of equal areas. Okay. You can see this is 2 is to 1. So the height, this height is 1/3 the height of the triangle. This is 2 is to 1. So this will the same will be for height. Okay, 3 is to 1, so 3 is to 1. Base remains the same, so we must remember this also. I may have forgotten it, that if you form a triangle and if G is its centroid, G is centroid of this triangle. So area of triangle ABG is area of triangle BCG is area of triangle CAG is 1/3 area of triangle ABC. Maybe I don't actually recall that I explicitly told you. So even if I told you, it will be a revision or just, we should keep this in mind. We should have done while dealing with similar triangles only, but maybe probably I didn't remember maybe. Fine. Further, if somebody is asking you, see, further this too is can be proved like this, see, the converse of midpoint theorem. If D and E bisect, for simplicity let us say bisect AB and AC respectively, then DE is parallel to BC. Okay. Midpoint or same ratio, suppose somebody says. So we simply extend it, suppose. Okay. We extend it to points at the BC and say DEF are equal, and then we join it. Now, oh sorry. Okay, we extend it like this. So are you able to see something? See, or you can draw something parallel to this and then extend it. Anything will work. See, suppose DE and EF are equal. Suppose we extend it like this. Okay. There are various ways to deal with. Suppose D is okay. These two are already equal. So this angle and this angle are definitely equal. So it's these two are equal and parallel to. Why? Because this angle will be equal to this angle by congruent. So these two are therefore parallel. Okay. Now okay, equally. So this becomes a parallel. Parallel. How come these angles are equal? Hmm. This is parallel to this, fine. And then we have to show that these two are parallel. So angles would suffice. Fine, 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 fine. Okay, okay. These two are already parallel. So this angle is equal to this angle. Okay. So this third angle is going to be equal to this angle. So since these two angles are equal, they are going to be parallel. Fine. So lot of things are done using the notion of diagonals bisect each other in a parallelogram. Okay. Now if you move ahead to say special quadrilaterals like say rectangle, rhombus, square. Okay, so in a rectangle the diagonals are equal in length. Is a parallelogram in which diagonals are equal in length. All the angles are right angles. In a rhombus, it is a parallelogram all whose sides are equal in length. So diagonals bisect each other at right angles. And in a square, all four sides are equal. It is a rectangle, special case of a rectangle as well as a rhombus. Of course, special case of a parallelogram too. So we are simply shrinking the set. Larger version would be your uh, trapezium. Say, trapezium, we have a family. In the family of trapeziums, we have parallelograms. Further inside it would be, very sorry, rectangle, rhombus, square. Sorry. So in a rectangle, diagonals are equal. So in a parallelogram, if diagonals are equal in length, it becomes a rectangle. In a parallelogram, if diagonals are perpendicular, it becomes a rhombus. In a parallelogram, if diagonals are perpendicular and equal, it becomes a square. Okay, but bisection is a very, very important tool. Okay, Here diagonals are equal in length and they are bisecting each other. This angle is not 90 degree. Okay. Here diagonals, of course, because it is a parallelogram, diagonals bisect each other. Okay. They are not equal in length. In a square, diagonals are perpendicular and equal to each other. Bisection plays an important role. If somebody says, suppose somebody says, in a quadrilateral, diagonals are equal in length and are perpendicular to each other. Then it is a square. True or false? Okay. So see, I am drawing two lines which are perpendicular to each other and are equal in length. Say this is A, B, AC is equal to BD and AC is perpendicular to BD. Okay, now you can very easily see that it is not a square. So bisection, I have emphasized it for say last 15, 20, 25 minutes that bisection is a very important tool. Property is a very important tool in solving problems and is a very intrinsic and important property of something being a parallelogram. See, of a quadrilateral being a parallelogram. So bisection plays an important role. Otherwise, if they bisect each other, so bisection in a parallelogram, we told, in a parallelogram, if diagonals are equal and perpendicular, it is a square. In a parallelogram, if diagonals are equal in length, it is a rectangle. In a parallelogram, if diagonals are perpendicular, it is a rhombus. Fine. All the sides of a rhombus are equal in length. Okay. So please keep this in mind. Fine. Similarly, see what we say is also to be kept in mind is that the quadrilateral formed by midpoints of sides of any quadrilateral is a parallelogram. So what we are saying is that if you take any quadrilateral then the quadrilateral formed by midpoints So we have to say PQRS is a parallelogram. What we can say is that SR is half of AC and PQ is also half of AC. SR is parallel to AC and so is PQ. So one pair of sides are equal and parallel. Hence, this is a parallelogram. Okay. Fine. We could have done it for the other also. You can similarly show that other pair of sides too are parallel by joining B and D. So please keep this in mind. That one pair of that in any quadrilateral, the quadrilateral formed by midpoints of the sides is a parallelogram. Now moving ahead, okay. Suppose I would say given 3 non-collinear points in a plane, how many parallelograms can be drawn three of whose vertices are these 3 points. Okay. So you are given, suppose I am saying you are given 3 points. And we have to draw parallelograms, 3 of whose vertices are these points. So you can safely say, see what is the situation? See, you have 3 line segments being provided. You can treat these 3 as 2 of them as sides and 1 of them as diagonal. Suppose I draw this one. See, one very obvious one is this one. Okay, this is a parallelogram. We have taken these 2 as sides and this as diagonal. Now suppose somebody says I take these 2 as sides and this as diagonal. Okay, so what are we going to get? Let us use a different color pencil. Okay, so this is the parallelogram. Okay, these 2 are sides and this is the diagonal. These 2 are sides and this is the diagonal. Now these 2 being sides and this being diagonal. So suppose these 3 points were A, B, C, P, Q, R. Okay. These are the 3 parallelograms that you are able to do. If you look at it very carefully, okay, if you look at it very carefully, are nothing but, see, and ABC are nothing but midpoints of PQR. Midpoints of PQR. Okay, and these sides are nothing but half of sides of this triangle. You can be asked further questions. Suppose area of this triangle is delta. What will be the area of triangle PQR? They are just twice the sides, 4 times. Okay. Now somebody may ask you, see medians. See, please keep these things in mind. Okay. Median of, suppose we draw these two triangles. Okay. What we have done is that we have taken midpoints. Okay. Now, see, look at it very carefully. This sides of this triangle DEF are half the sides of triangle ABC. So, area of triangle, we must area of DEF is 1/4 area of triangle ABC. You can say BDEF, this is a parallelogram. BFEC is a parallelogram. AFDE is a parallelogram. Further, what you can possibly see is that, see, if you draw medians of the original triangle, what you can see for DEF, what will they be? So you can see that since these are parallel, okay, if this is x, this is x, this is x by 2, and similarly this is x by 2. So this is median. This is median for triangle DEF also. This line you can see. See, if this is x by 2 because this is bisection, and these are parallel definitely. This is x by 2. So centroid of DEF coincides with centroid of ABC. They have same centroid. Okay. Further, somebody can also ask you, see, okay, if we are drawing it, let me complete today's lecture using this say. Suppose these are midpoints. D, E, F. Fine. Now, if you look at it, see, if I draw perpendicular bisectors of ABC, perpendicular so this point O is what? O is circumcenter of ABC. And if you look at it very carefully, it is the point of intersection of altitudes for DEF. Are you able to see? See, this is perpendicular, these two are parallel. This angle will also be 90 degrees. So O is orthocenter of DE. So just we will keep, once we come through, go across circles, then also we'll come across new results. But as of now, the purpose of today's lecture was to come to quadrilateral and then some properties of triangles as has been deduced. See, a very important property of parallelogram: diagonals bisect each other, necessary as well as sufficient. That is the crux of today's lecture. A lot of theorems you would be requiring this elementary property of parallelogram in solving problems, in proving theorems. So please keep this in mind, apart from definitely other well known facts. So I hope, starting with quadrilateral and then ending with some properties of triangle, this session would have been beneficial to you. You would have gained something worthwhile from this session, and you will keep on encouraging us, you will keep on joining us, so that we are able to share whatever little we know of mathematics and help you in cracking, apart from cracking the exam, help you in loving the subject of mathematics, especially the beauty of geometry. So on occasions we are very good at algebra. Geometry requires some very fascinating skill set, quite different from algebra. Once you start loving geometry, it's altogether a different experience. It on occasions gives you goosebumps when you are able to solve a beautiful problem of geometry using geometrical notions. Once we have gone through circles and angles using, you would simply, if you are continuously putting in efforts, you will simply in love. That is my experience. All any student who goes through that phase, he or she will simply be in love with the chapter of geometry, particularly geometry. Okay, so I hope you would have again you would have seen some of the facts and learned something. Okay, thank you very much.